Okay, so we have this structure here, kind of some sort of bar that got a handle at the end, and this fellow's pulling on it. For some reason, it doesn't actually appear to be doing anything, but you know. So he's pulling on it at the end with a 500 Newton force. Um, it's got this cable that's kind of preventing the rotation about B, and we're taking a section cut at A here. So section cut at this segment right here. The cross section at that point looks like this. And we want to figure out what the stress is at this point, A, that is kind of just below the web of the topmost piece there. So back to basics. First thing we're going to need to do is do a bit of equilibrium problem. So again, got a free body diagram here of our structure. So we're pulling down on it, we're pushing up on it with the tension here, and it's that tension there is also going to cause an axial force pulling towards the wall. So we're going to have a reaction B in the vertical direction, By, and we're going to have a reaction Bx. So we also know that Cy and Cx are related because of the orientation. You know, the forces only act in the direction of the wire. So we can solve for Cx in terms of Cy. So Cx just is equal to 1.732 times Cy when that angle is 30 degrees. And then we need to basically take a moment about B to help solve this. So if we take a moment about B, Bx, By, and Cx don't come into play because they all pass through B. So the only forces there that matter at all are going to be Cy and the 500 Newton force. So again, Cy times 300 millimeters minus the 500 newtons times the 650 millimeters between the wall and where the 500 newtons is applied is equal to 0. So we can solve for Cy as 1083.333333 newtons, which means that we can solve for Cx by multiplying that by 1.732, which gives us a Cx of 1,876.333 newtons. So we can solve for By then next. So By, it can be solved for by taking the sum of the forces in the y direction. So By plus the 1083 minus the 500 gives us, actually that's equal to 0, and then Cy is equal to, sorry, By is equal to negative 583.3333 newtons. So that one's actually acting downwards. And then obviously Bx is equal to Cx because there's the only two forces. Bx is equal to Cx. Also did a few calculations on the cross-sectional area. So we know that we're going to need to figure out its Iz. So again, using the usual coordinate system that I like to use, x is along the length of the beam, y is vertical, so z is this way if we're looking at the cross section. So IZ, that's just going to be equal to kind of the I of the overall thing minus the I's of this cross section here. So 1 over 12 times 50 millimeters to the third times the 20 millimeters minus 1 over 12 times the 35 millimeters to the third, because that's the distance from here to here, times the 12.5 millimeters that are left when basically this 20 millimeters minus the thickness of that web there. Sorry, of that so of the web. So that gives us 163.7 times 10 to the 3 millimeters to the fourth. Also going to need the area. So again, 50 millimeters times 20 millimeters minus 35 millimeters times 12.5 millimeters. That'll give us 562.5 millimeters squared. So that's relatively straightforward. So I'm just going to graph our shear diagram. So again, I'll just kind of redo our free body diagram real quick. So again, we're pushing down on it. And then so scroll down a bit too much. Come on. So again, so for a shear body diagram, we kind of start out with a negative 583 newtons. That continues for the first 300 millimeters, and then it jumps up when that 1083 newtons gets applied, up to 500 newtons, and that stays constant until you hit the handle, and then it jumps down. The normal force is even more straightforward because again, there's compression because of Bx until you get to Cx, and then so in between there, the compression is 1,876 newtons, and then beyond that, it's nothing. There's not going to be any compression in this segment of the handle. And then the moment diagram is fairly straightforward. Again, we know that the way this beam is supported, it's free on one end and it's got a pin connection on the other end. So you know that these endpoints here, those both need to be 0. So and then we know that the shear is constant for these sections. So you just get a linear rate. It decreases because this is negative shear till it hits the point where the cable is attached. Then it starts increasing back up, and then it hits 0. So the magnitude of the moment at the point where the cable is attached is negative 175,000 Newton millimeters. So the point that we're looking at, however, that's halfway between B and C. So basically we know that it's going to be half that. So the point that we're examining has a moment of negative 87.5 Newton meters, or negative 87,500 Newton millimeters. So from there we can calculate the stresses that are acting at AR. So we get the bending stress. So the bending stress, again, is the negative moment times y over I. So again, the moment itself is negative, so those negatives cancel out. So we got 87,500 Newton millimeters times the 17.5 millimeters that is from the centroid to here. Yeah, that's 17.5. Divided by our I of 163.7 times 10 to the 3 millimeters to the fourth. Yeah. So based upon that, again, just canceling out our units properly, got the millimeters, got 2 millimeters on the top that cancel out cancel out all but 2 of the millimeters on the bottom, leaving us with newtons per millimeter squared, which is a megapascal. So plug those numbers in, and we end up getting 9.35 megapascals. So for the shear calculation, we've got shear is equal to V times the Q over IT. So V in this situation is 583.3 newtons. The Q is just based upon, so again, we got this section here. So it's just based upon the area that I kind of just cross section. So again, the width of that is 20 millimeters. The thickness of that is 7.5 millimeters. And its distance from the centroid is just going to be 20. The centroid's in the center, so from the center to the top is 25 millimeters. So from the center to the centroid here is going to be that 25 millimeters minus half the thickness of the flange there. So minus half of 75.5, which is 21.25 millimeters. So that gives us a Q of 3,187.5 millimeters to the third. And then thickness, for the thickness, again, we're just basing that upon the thickness of kind of the area we're looking at here. So we're looking at that area there. So we are going to be using 7.5 millimeters. So plugging in numbers over here, that gives us, with everything canceling out, to units cancel out to newtons per millimeter squared, and we end up getting a shear stress, transverse shear stress of 1.551 megapascals. So next up, our normal stress. So our normal stress is just the load divided by the area. So it's a compressive load in this instance, so it's a negative value. So negative 1,876.3 newtons divided by 562.5 millimeters squared gives us negative 3.34 megapascals. So let's orient ourselves on a cube here. So again, we are looking at this little section here, A. It's right below the flange. So if we want to kind of look, so the shear stress, let's start with the shear stress. So again, we know that kind of on this end of the beam, we got a load that's pushing downwards. So that'll kind of continue on until we hit this cube here. So that means on this face, the shear load is going to be pushing downwards, which means that on this face, the shear load will be pushing upwards. And obviously, those two need to be in that direction as well. So again, that means that this here is a positive shear stress it's a positive shear stress on the positive x face because it's pointed in the positive y direction. This is x, that's y, direct, z goes in this direction. As for the stresses in the x direction, we got the bending and our normal. So the bending was the bending was 9.35 megapascals, and our normal stress was minus 3.34 megapascals. So that gives us a axial a stress in the x direction of 6.01. And then there's nothing acting in the nothing acting here in the y directions. So start off, figure out where our center is. So sigma x plus sigma y over 2. So 6.01 plus 0 divided by 2, 3.01 megapascals. Our radius there, again, it's just the 3.01, which is the difference between the center here and this point here. I guess it's 3.0. Anyways, whatever. That extra 0.01 isn't really going to cause big difference. And then the y component there is, the shear component there is 1.51. So that squared plus that squared, square root, gives us a 3.37 megapascal. So we can plot our Mohr circle here. We're placing the center at 3.01. The radius of this is 3.37. So again, that'll be like, that means that our maximum here and here, that's also 3.37. And the one point that I'm graphing here that we know on the positive x face here, because again I like to use that positive x face to right here to define our points. So that's this point right here with a positive normal stress of 6.01 and a positive shear stress of 1.51. So again, remember that positive is down on this graph, on your Mohr circle graph. So that's right there. So we need to figure out how it rotates. So that'll be just based upon what this angle here in the middle is. So 2 times our theta prime is equal to the inverse tangent of 1.51 divided by 3.01. That gives us an angle of 13.3 degrees. And again, we know that we're starting at this point here and we're trying to get to this point here. So we're going to have to rotate, and we're going to have to rotate 13.3 degrees counterclockwise. So kind of starting with a square, rotating counterclockwise gets us a square like this. And as for which stresses are on which face, well, again, this stress here started with the 6.01, and when it rotated a little bit, it increased a little bit. So that means that this face corresponds to this face after rotation. So that means that this direction here is the 6.38 megapascals. That is our prime stress. Again, that was calculated just based upon the center plus the radius. And then here we've got our compressive stresses that would be induced, the 0.36 megapascals, which was calculated just based upon the center minus our radius from here to here. We can also figure out where the maximum shear stress is. So if, for example, we instead rotated, let's say we rotated an additional 45 degrees up to 58.3 degrees, that'll get us to a point where that'll get us from here up to here. So we're rotating all the way up this way. So that means that essentially the stresses are the normal stresses are all going to be 3.01 megapascals tensile on all four faces, and then we're going to have the same shear stresses on all four faces as well. So that'll be 3.37 megapascals. As for the directionality of that, again, just keep in mind that when we had our original square, that had a directionality that was going this way. And then we rotate this thing up 48 degrees. So that this face here corresponds to this face here. So what happened to the shear, however, so the shear started out as positive, and then it got to negative. It got to its maximum negative value. So that means that the directionality of our shear on this face again is like this, because started out pointed this way. I guess, sorry, I had my head covering a bit of it. So it started out pointed this way. We rotated, so this face, it corresponds to this face. We rotated, and the directionality on that face flipped. So we're going this way now. An alternative way you could have done this would have been to rotate the cube instead of 58.3 degrees counterclockwise. You could have rotated 31.7 degrees counterclockwise. So again, that would get you to the same shape. And then again, for directionality of the stresses, what that would mean is that if we'd started out with a positive shear on this face and then rotated this way, this face would correspond to this face, and it would just grow. So that would mean it wouldn't change directions. So that would mean we'd still have stresses, the shear stress in this directionality on this face here, which of course means that we have stresses there, and stresses there in order to keep everything balanced, which is not too shockingly the same result that we got if we had rotated 45 degrees the other way instead. So, got to the same result two different ways. And that is that.